Hey everyone, welcome back. This is lesson 3 in our Unit 7 solutions. Today's lesson is called Factors Affecting Solubility. So in the last video, we covered Table F and solubility guidelines and how to use them, how that works. And today we're going to be talking about different factors that affect solubility. And so again, just to recap the definition of solubility. So if you were to look this up in a textbook, you would get solubility is how much of a given solute dissolved in a given amount of solvent at a given temperature. So we have a bunch of words: solubility, solute, solvent, and they all kind of look the same. So remember, solute is the thing that gets dissolved. Solvent does the dissolving. So basically, solubility is how much stuff can be dissolved at a given temperature. Okay, so what I want you to do right now is think. You have 6 different things: temperature, stirring, pressure, nature, solute, solvent, particle size, and surface area. I want you to categorize these words. Do you think they fit in the affects rate column or the affects solubility column? So will it change the time it takes to dissolve or the amount that is dissolved? So go ahead and try to put those words where they belong. Okay, so if we're talking about affects rate, or to start with solubility actually, temperature affects solubility. So changing the temperature, you can change the amount of stuff that gets dissolved. Stirring only changes the speed at which something dissolves. It doesn't change how much gets dissolved, it just, the more you stir, the faster it gets. The nature of the solute and the solvent, that actually affects how much can be dissolved. And so can pressure. So pressure, temperature, nature, solute, solvent, that predicts, or that affects really rather, the effects of solubility. So it changes how much is able to be dissolved. Whereas stirring, particle size, and surface area, that affects the time it takes, or the rate it takes to dissolve. So we're going to cover all of these in a little bit more detail, but again, these are super important. Okay, so let's talk about temperature. So I have 3 questions for you. What happens in terms of solubility when we place a tea bag in hot water? What happens when you place a tea bag in cold water? And if I order coffee, if I order hot coffee and 2 sugars, all the sugar is dissolved. But if I order iced coffee, all the sugar is on the bottom. So, with those 3 questions in those scenarios, what do you think the relationship is between temperature and solubility? So, to kind of answer your questions, or that your thoughts, temperature for liquids and solids. Again, gases is different. For liquids and solid, if you increase the temperature, more stuff can be dissolved, so the solubility increases. The lower the temperature, the less solute that can be dissolved, so the solubility decreases. So again, if you have hot coffee, it's able to dissolve the sugar a lot easier. If you have iced coffee, not as much can be dissolved. And we'll get into table G on the reference table, and that kind of goes into that in more detail. Now, note this is the exact opposite for gases. So for gases, high temperature is low solubility, and low temperature is high solubility. Again, these are things that we'll kind of point out again when we get to table G. Now, let's talk about temperature and fish. All these fish are dead. So what do you think happened in terms of temperature and solubility? So now we're going to kind of focus more on the gas. I kind of just touched on that. So what do you think happened in terms of temperature and solubility of all the gas that was dissolved in the water? Okay, so here is the gases. And so with increased temperature, you have less gas dissolved. And so that gas solubility decreases. So gas actually can be dissolved. If you've ever opened a can of soda, you kind of know this. If you have a warm soda, there's that you have in a cup, it's not very bubbly, it's very, very flat because all that gas that was in there left. But if you have a nice ice cold cup of soda, it's very, very bubbly. You have more gas dissolved, so you have higher gas solubility. So for gases, think about, a warm soda versus a cold soda. And for liquids and solids, think about dissolving sugar in your tea or your coffee. These are all things that you've experienced. So if we're talking about more pressure, we're talking about the soda can. And so, what do you think the relationship is between pressure and the solubility of gases? So with the increased pressure, you have higher gas solubility, and with less pressure, you have a decreased gas solubility. So what this means, when you increase the pressure, the gases are being forced to be dissolved into that soda. So if you have a can of soda and then you shake that can of soda, every time you shake it, you're creating more and more and more pressure. Now, as soon as you open those cans of soda, let's go back to this picture, you're releasing that pressure. And so all of the gases can be, released. So if you have an increased pressure, and so this is why when you shake cans, they explode. When you're increasing the pressure inside the can, get more and more gas is being dissolved and into that soda. When you open up, there is such a huge pressure difference. And so once that pressure is released, that gas is like, bye, I'm out of here, and flies out. So that is why when you shake a can of soda, it explodes. You have that bigger pressure difference. So pressure and gas solubility also has another really cool real world application called the bends. Now, if you're a scuba diver, you've definitely heard of this. And so in your bloodstream, you have a whole bunch of, gases in your blood, oxygen, nitrogen, all these other different things. So when you dive deep into the water, the pressure, again, the deeper that you dive into the water, the more pressure you have kind of pushing on your system. And so the deeper you go, the pressure increases. So that gas in your blood is being more and more dissolved into your bloodstream, which is that's okay. But when you come up and you're relieving that pressure, if you come up too quickly, just like opening the soda can, all that gas that has been dissolved in your blood comes out. You have these gas bubbles traveling around your body, which can lead to not so good things. And so, with that, and that's known as the bends, these gas bubbles kind of end in your joints in different areas and cause you to literally bend over in pain. Now, to avoid this, divers are very much familiar with this table. Depending on how far deep you dive, you have to gradually release that pressure. So gradually swim up and kind of say you're, I don't know, 40 meters down. It's probably a lot. You come up a few meters, chill there for a little bit, let your body equalize. Go up a few more meters, chill out, let your body equalize. Go up a few more meters, chill out, equalize until you're kind of back at that sea level. So again, depending on how long you're there, it tells you how long you need to kind of be at each checkpoint. So whales do this too, or a whole bunch of marine mammals. There is actually evidence of this beaked whale. Now it's meant to dive down 3,000 meters, which is way, way more than us humans can do. But there's evidence of these whales getting the bends because they get scared with different shipping noises and they shoot right up. So the whales know to kind of not dive directly up really, really quickly, but sometimes they get scared because of stuff humans do and they end up getting sick and dying. Okay, so moving on, talking about agitation and stirring. We can also kind of add shaking here too. So if you're making strawberry milk, I'm not a fan of chocolate milk, so let's say strawberry milk. Or if I pile sugar into iced tea, should I just leave it there or should I do something? Why? And so the trend here is that if you increase this stirring or this agitation or this shaking, you're increasing the rate, so the speed of dissolving. So if you have that protein drink or, sugar in iced tea or that chocolate milk example, everything will eventually dissolve, but if you shake it or stir it, it dissolves a lot faster. Now, this does not change the solubility. So just because you stir it doesn't mean you can dissolve more, it just dissolves faster. So again, here we have ground sugar and cube sugar. Which do you think will dissolve faster and why? And so the answer is the increased surface area, increased rate of dissolving. There's more that's in contact with the solvent, the thing that does the dissolving, so it can dissolve faster. Again, this is the rate, it dissolves faster. It has nothing to do with the actual amount of stuff that can be dissolved. Okay. Here we have the nature of solutes and solvents. And so one of the most important things to remember here is like dissolves like. So here we're talking about the polarity of the molecules. So what like dissolves like means is that something that is polar dissolves something that is polar. Something that's ionic dissolves something that's ionic. Now, polar can dissolve ionic things because they have that kind of those charges. That's not the most important thing. Then you have, nonpolar dissolving nonpolar. So things that are the same polarity will dissolve other things of the same polarity. And so here you have a polar bear saying, "Help, help, I'm dissolving." And then the brown bear goes, but bears are insoluble." And the polar bear goes, "That's easy for you to say, you're not polar." So there's your polarity solubility joke. Ha 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 ha. Okay, so if we think about an example you've probably seen in real life, salad dressing or something like this, using the concept of like dissolves like, do you think oil will mix with water? Explain in terms of polarity. So I gave you this picture. Do you think oil dissolves in water? And I want you to explain your reasoning in terms of polarity. Okay, so we know water is polar. H2O is polar. And based on this picture and based on other experiences you've had in life, oil and water do not mix. And so if we know like dissolves like, if oil was supposed, if we want to figure out the polarity of water, of oil rather, and it dissolved, we would know oil is polar. But because like dissolves like, but because oil does not dissolve, it can't be polar. So that means oil has to be nonpolar. And so when you have two opposite things, that is things that don't dissolve. Okay. Particle size. Which of the ground sugar and the cube sugar do you think will dissolve faster and why? So go ahead and answer this. And so the smaller the particle size, the increased rate, again, we're talking about the rate, so the faster, the dissolving is. Again, this does not affect the amount that can be dissolved, it just affects the rate of it. So just a quick review of relationships. When we did our gas law unit, we covered this a lot. Just remember, inverse relationship, one variable goes up, one goes down. So you get that nice little curve. And that's, your Boyle's law. But again, inverse relationships, you have that same shape, one up, one down. And then direct relationships, one goes up, the other goes up, or one goes down, the other goes down. They do the same thing. And to kind of using this, that's how we'll kind of sum up everything that we've talked about today. And so, kind of our wrap it up chart, this is the entire PowerPoint in one slide, talking about what happens where. So this is a good point to probably pause the video, write this down if you're interested, but this is kind of the entire lesson in one slide. Okay, so that's pretty much it. On the next episode, we will talk about table G and solubility curves and kind of take a closer look as to how temperature affects solubility. But for right now, that is it. Have a wonderful day. Bye.